Hello everybody, welcome to 9.3 Ellipses. So today we are going to learn how to identify key features of ellipses and use them to solve problems. Alright, so first of all, what is an ellipse? An ellipse exists where a cone is cut diagonally through both sides. So in other words, if we take a cone and we cut it not perfectly across, right, not horizontally, but if we cut it diagonally, it'll create a shape that is taller than it is wide or wider than it is tall. It's not going to be perfectly circular, and that gives us an ellipse. All right, so let's look at key features of an ellipse here and give it some mathematical definitions. So first of all, we have two axes, right? Our first, in this case, is going to be our major axis, which in this case is our horizontal axis. Now this whole thing could be turned, and our major axis could be vertical. In this case, our major axis is horizontal. The distance from the center to the vertex we call length A, and the point from the center to the co-vertex, which is on the minor axis, is what we would call B. And then we also have these other points, which you'll notice here are points F1 and F2. We call these foci, and the foci are points that we can use when we're actually constructing the proof for how ellipses are formed. We can pick a point P on the ellipsis itself, and we can actually form a right triangle between the two foci. And there's a whole breakdown into how we get the formula that I'm about to show you. But we use these foci for a few key reasons, but being able to identify where they are is important to some of these problems. So just know that A is the distance from the center to the vertex, and the focal length is the distance from the center to the foci. So in this case, the distance is going to be horizontal, and it's going to be always a little bit less than the distance of A. It'll be contained within the ellipse. All right. So, standard form of an ellipse. Now, remember how I told you before we have major axis and minor axis? If the major axis is vertical, that means that your ellipse is going to be taller than it is wide. So in other words, if we have a vertical major axis, our ellipse is going to look more like this. And you'll notice that in our formula, we have x minus h squared plus y minus k squared, but under the x minus h, we have b, and under the y minus k, we have a. And this is because a shows us which one of these is the major axis. You'll notice that under horizontal major axis, right, the a squared is under the x, which means that this is going to be wider than it is tall. So it'll look a little bit more like this, which is what we had in the picture before, right? And then of course, as always, our center is h comma k, where h is the horizontal shift and k is the vertical shift. All right, and then the last thing we're going to need to know is when it comes to establishing the focal length, remember that A is our major axis length, B is our minor axis length, and to find the focal length, we find C. And if we use this formula here, B squared plus C squared equals A squared, we can solve for it. Actually, if you want to rewrite this formula, kind of just using the same logic we'd use as Pythagorean theorem, we can actually say that C equals the square root of A squared minus B squared. Right? It's a little bit different than the Pythagorean theorem because in this case the C is on the left, right? But it kind of looks similar. So we can use this formula here, the C equals the square root of A squared minus B squared, to find the focal length. All right, so let's jump into a problem. You're going to notice we're going to use some stuff like we did in circles, where we're going to have to complete the square and things like that. So write the equation of an ellipse and define its key features if 2x squared minus 12x plus y squared minus 2y plus 15 equals 0. So the first thing we're going to do is we're going to rewrite this equation, and we're going to get it into a form that looks like this down here. All right, and then once we get it into a form that looks like that, we can identify what our A and our B are, and then we can find all of the points and go from there. So, all right, so let's start off with the equation. So we have 2x squared minus 12x, and then we also have the y squared minus 2y, and then the plus 15. The first thing we're going to do is we're going to get this 15 out of here. So we're going to subtract 15 from both sides. So you'll notice that's what we do. And then we're also going to group together our x values and our y values. And then what I went ahead and did in this first step as well is, you see how we have a 2x squared minus 12x? I went ahead and just pulled a 2 out of each of those. That way we can just have an x squared and a y squared with our leading coefficients being 1. So we don't have any numbers in front of our x or our y. So I pulled out the 2, I separated our x's and our y's, and I subtracted the 15. Just kind of did that all in one step here. All right, now for step 2, right, we have to complete the square for both x and y. So if we complete the square, we use this little formula. I'll write the little formula over here for you, even though we've used this 100 times at this point. So we have b over 2, and that whole quantity is going to be squared. And this is the formula we're going to use to complete the square, right? Complete the square. Okay, so if we do this for our x value, we have -6. -6 divided by 2 is -3, and -3 squared is 9. So you'll notice that we added 9 to this side, which means we also would have to add 9 to this side, correct? But remember that we factored out this 2 initially. So because we factored out this 2, even though we're only adding 9 to this side, it's as if we're adding 18 to this side, right? Because we're actually adding 2 times 9, which is why we add 2 times 9 to this side. So if you're wondering why this is being multiplied like this, it's because we're adding it to a binomial, essentially, that's already being factored. So we have to account for that factor. All right, now when it comes to our y side, we have y squared minus 2y plus 1. The reason why we added 1 is because if we take our -2, which would be our b value of this trinomial, we put in the -2 here, we have -2 over 2, which would be -1. -1 squared is just +1. So that's where we get this 1, and of course we add that to both sides. All right, so if we simplify, the x squared minus 6x plus 9 will reduce into x minus 3 squared, right, when we condense it. And then the y squared minus 2y plus 1 will condense into y minus 1 squared. If you don't know how I got that, essentially all I'm doing is I'm just factoring it, right? I'm breaking it down into its pieces, and you'd get x minus 3 times x minus 3 if you factor it, which would be x minus 3 squared. If you need help with this, come see me. I'd be happy to show you how to do it. So we have 2 times x minus 3 squared plus y minus 1 squared equals 4. When we simplify all this on the right-hand side, we just get 4. And then you'll notice that in our form here of our equation, everything is always equal to 1. And that's because anytime we would have a number over here, we actually have to divide the other side by that number so that we can turn this into a 1. So even though we have a 4 over here on the right, we actually have to divide both sides by 4 so that we can get this side to equal 1. So let's do that. So if we divide both sides by 4, you'll notice that we get, I'm kind of separating the 4s into these two pieces. We could put it all over 4, but it'll be easier to look like our form if we just kind of break it off into the two pieces that are being added together. So on the left, I have 2 times the quantity x minus 3 squared over 4. And then on the y side of things here, we have y minus 1 squared over 4. And that all equals 1 now because we divided both sides by 4. And then all I did was I took the 2 and divided it by the 4, right? Cut these two pieces out. So the final product here, or the final result, is x minus 3 squared over 2 plus y minus 1 squared over 4 equals 1. Okay, so this is our formula, right? This is what we're looking for. Now we can use this formula to solve for our key features. So our key features are going to be the center, the vertices, the covertices, and the foci, right? And if we go back up to our picture, the center is this point here, right? The vertices are these two pieces here, right, which are a distance from the center. Our covertices are on the minor axis, and they are b distance, the distance of b away from the center. And then remember, the foci are from the center to these f1 and f2 points, and the focal length will be a length of c. Okay, so let's do that. First of all, let's look at our center. Remember that our center is just simply the point h comma k, which we've used extensively at this point, right? So if we look at our formula, we have x minus 3 squared, and remember that this 3 would then be our h, and then we have y minus 1 squared, and this 1 would be our k. So our center is simply 3 comma 1. This essentially means that the entire ellipse has been shifted up 3 and 1 to the right? Okay, so our major axis, remember if we go back over to our formula, remember how we said that whichever of these has A is going to tell us which one's our major axis and which one's our minor? Well, in this case, we also have to identify that A is always going to be the larger of the two numbers, right? So if we go back over here, right, we have x minus 3 squared over 2, and then we have y minus 1 squared over 4. So this 4 being bigger than this 2 tells us that this is actually going to be a horizontal major axis, or sorry, a vertical major axis. It's going to be taller than it is wide, right? So when we look at this, right, well, we know that, okay, we know that 4 is now 4 is a squared, right? So if we know that 4 is a squared, we know a is 2, which means that the vertices are going to be up 2 and down 2 from the center, right? If you can imagine this ellipse here, right, if we flipped it and it was now going up instead of like side to side, then A would now be the longer distance here, and the focal length would be C, which would be a little bit less than A, right? So if we start with just our vertices are the distance from the center to A, right? Which in this case would be up and down because we have a vertical axis, or a major vertical axis. So we're going to essentially be going up 2 and down 2 from our center. So if our center is at 3, 1, and we go up 2, it would give us 3, 3. And then if we have 3, 1, and we go down 2, we'd be at 3, negative 1. Okay, so we're going to do the same thing now for the horizontal axis for B, but we're going to be going horizontally because B is the minor axis, right? So let's look at our horizontal distance. So we're going, if we look up here, B squared is 2, right? So if B squared is 2, then B equals the square root of 2, right? Which means that the covertices are the square root of 2 left and right at the center. All right, now I'll tell you that the square root of 2, to make this a little bit easier, just so I can show you what's going on over here, the square root of 2 equals approximately 1.4. It's like 1.41 or something like that. So it equals approximately 1.4. So if we look at our covertices, don't even worry about these first two, right? I'm just going to show you with the math. Remember that the covertices, because we have a vertical major axis, the covertices are going to be horizontal. So now when we go to our center, we're going to be affecting our x value, not our y value, right? So we're going to be going 1.4 to the left of 3 and 1.4 to the right of 3. So if we look at our answers over here, right, 3 becomes 4.4, comma 1, and 3 becomes 1.6, comma 1, both of which are 1.4 away from 3. All right, so the final thing we need is our foci, right? And remember, our foci are C units away, and our focal length, which is C, is going to be using this little formula that I showed you. So this is C equals the square root of A squared minus B squared, right? And remember that in this case, A squared is 4 and B squared is 2. So we're going to do the square root of 4 minus 2, which equals the square root of 2. So in this case, C is actually the same as B, which is kind of nice because it makes we already know the math, right? We know that the square root of 2, I'll just like write this over here. We know that the square root of 2 equals approximately 1.4. And now we can do the same thing, remember? But the foci are always on the major axis. So we're going to be going the same direction as A. The foci and A will always kind of line up with each other. So C and A will line up and B will kind of be the other one. So remember in this case, our A is on the vertical axis, right? So in other words, we're going to be going up and down from the center a distance of 1.4, which is our focal length, which is also C. So if we start at 3, 1, because that was our center, we're going to go 1.4 up and we're going to go 1.4 down. So if we start at 1 and we go up 1.4, that's going to give us this number here, which is 3, 2.4. And then if we go 1.4 down from 1, we're going to be at 3, negative 0.4. All right. Oh, actually, this should be 3, negative 0.6. Math is hard, guys. Let's change that here. All right, so 3, negative 0.6. And there you go, right? So we took the 1.4 and we went up 1.4. And then from 1, we went down 1.4 and gave us negative 0.6. So these would be our foci. If you wanted to graph this, which we can just do for fun, right? So we're going to have our vertical axis, and we're going to have a horizontal axis. Whoop. Okay, and we know it's going to be taller than we are wide. And remember, we're starting at the center. This is usually the easiest way to do it. We're starting at 3, 1. So let's start at 1, 2, 3, 1. Let's go ahead and start right here. That'll be our center. And then our vertices are at 3, 3, and 3, negative 1. So, wait, 3 comma 1. Would help if I could plot this right. That's all right. We'll need those points anyway. All right, so 3 comma 1. So our center is here. There we go. And then our vertices are at 3, 3, and 3, negative 1. So 3, 3 would be our first vertex, which we can put, let's do it in red just like we did before. 3, 3 would be here. 3, negative 1 would be here. This would be negative 1. And then our co-vertices are 4.4 comma 1. So we can just add like a 4. So 4.4 comma 1, let's go with blue, would be like here-ish. And then this one would be 1.6, so just a little bit past 1. So let's say like here, somewhere like that, right? And then I know this is kind of small, so we can kind of like zoom in, see if we can get this a little bit more. But remember, our foci are going to be at 3, comma 2.4. So our foci are actually going to be like in between. At this point, it's going to be hard to draw just because of the scale of it. But like the foci would be like here and here. And then when we draw our ellipse, it would be like this, which is just a little bit taller than it is wide, which is what it should be, because remember that our A was attached to our vertical axis. All right. So yeah, I mean, if you drew this out a little bit bigger, like if you zoom in a lot or whatever, it kind of makes it a little bit more clear. But just because the numbers were so close together, it's kind of hard to tell, but this is definitely taller than it is wide. And that's it, right? This is identifying all of the key features of ellipsis, and it's understanding like the formula and how the formula shows us what those key features are. And it all stems from the idea of understanding which axis we're dealing with and how we can use the formula to identify all of our key features. So, all right, awesome. Well, that's it for 9.3, ellipsis. In the next video, we'll be doing 9.4, which are hyperbolas, which are basically like double parabolas that extend in opposite directions. So, all right, I'll see you there.